how Siemens looks at it. We've learned CCS is a very important, or the reduction of carbon dioxide emission is an important thing for humankind in principle. But nevertheless, only wise ideas and the human sense is not enough. We need to have a business out of that. But this is given, I will show you. And then I will show you how the Siemens expertise is given in order to make a storyline out of that. And then I will focus on the two major approaches of CCS, which is, as we've learned, IGCC and the post-combustion method of retrofitting with conventional power plants, where, as you've heard, I'm more the expert. And the last chapter is also some important, as we know from our customers, and they ask us, we do not know whether the CCS technology will be implemented, but we will be prepared. And so they ask us for a post-combustion ready design, so build a conventional power plant, but where it is easy to do retrofitting. So this chart once more showed what our problem is. Energy demand is rising and rising and rising. Especially in Germany, the government and the society wants to have more renewables. They want to change the energy mix. But this cannot be the whole story, even though we will be able, this is an ambitious scenario, to enforce here the renewable energy. Overall, in the next years, fossil-based power generation will be increased. So on the other hand, that means we will have to do something. And if we look now to the so-called renewables, there we have a quite encouraging picture what the levelized costs of future energy production mean. And if we look here at the numbers which are given for conventional power generation with CCS, we are here in the same ballpark. So CCS is, especially compared to some of the so-beloved renewables, are quite competitive. And that means for Siemens that we have a clear market and a clear goal to develop such a technology. In order to develop such things, multiple knowledge is necessary, and fortunately in Siemens we have the whole train and we have expertise in all fields of energy production, generation, but also on the things we need then for the CCS. But here we have the oil and gas activities, we have the fossil power generation, we have also wind power, solar, hydropower, energy services, power transmission. So in the end, whatever solution will be inside of Siemens, the healthcare, the automation was more industrially driven, and the power generation. And there we have the product, energy solution, information. And here we have the new technologies where the post-combustion, the fuel gasification, energy storage, and other new topics are located. So if we have a more close look on carbon capture, we also need some special knowledge, which is in fact at first the chemical engineering. As we have heard today, IGCT is not really energy power generation. This is really a chemical plant more or less, and this is also true for post-combustion capture. Nevertheless, you have to integrate that into the power generation environment. You need the knowledge to scale up these things. There we have the colleagues in Pittsburgh who are working on the FGD buildings and these things. We are able to simulate and to plan whole power plants, the need for the storage, the carbon dioxide compression. Of course, we need steam turbines, and in the case of gas-fired power plants, also the gas turbine. With regard to the chemical engineering, where I also belong to, this is located in the industrial park of Höchst. So my personal origin is the former Höchst AG. You may know Bayer, BASF, and Höchst were the former three big chemical companies in Germany. The Höchst AG had a spin-off, and from the chemical engineering department of the Höchst AG, in the end, Siemens part origin. We have about 200 colleagues there in Frankfurt, and we heard today that it's crucial for proper implementation or product development, not only to have researchers, but also to have the engineers. And above or among these 200 people, co-workers are engineers who build for a long time chemical plants and who are able to do a proper project development. So we come now to the measures, as you also heard yesterday. Of course, the most important or the nearest thing we can do is to rise the efficiency of the power plant in order to reduce the carbon dioxide emissions. There much effort has been done in the last years, and we've managed it to gain several points of efficiency. But now with carbon capture and storage, we will maybe come back to this point here. But on the other hand, to get here more efficiency will be a really challenge, because things are going more and more sophisticated in order to be successful to get here to better efficiency. The same is true for the gas-fired power plants. Here we have a higher efficiency, and although one should think that because of the composition of the flue gas from a coal-fired power plant and a gas-fired power plant, it should be always be sensible to start with a coal-fired power plant to do CCS. The clear development in Europe is that the existing projects go towards gas-fired power plants. And not only in Europe, also in the Middle East, where we are dealing with the enhanced oil recovery. So, as we've learned, in principle, we have three major routes how we can approach CCS. This is the IGCC, which we have heard in the morning here. This is the post-combustion, CO2 scrubbing, and what we directly heard before, the oxy-fuel. Siemens goes the two ways via the post combustion CCS, which is developed for the gas-fired and also for the steam-fired power plant. And here we have the amount of CO2 reduction which is possible here. And the other route which we are dealing with is the gasifier technology, which I will in the Netherlands we have also a reference where we already have this coal-based IGCC power plants with integrated Siemens technology. The major advantage, I guess we haven't discussed this so far, of the IGCC, how we see it, is that we have a high flexibility with the fuels, and we have beneath the energy production or generation also that we can produce chemicals. It makes our customers quite flexible and to fulfill their needs. So today we see the fully generation, CO2 capture and enhanced oil recovery that together makes a strong driver for our customers. Here is the main product of Siemens, this gasifier. Quite interested in the main data here. This is the environment. So the basic know-how is here. Heat equipment delivered by Siemens gasifier. So we are buying the air separation unit, fuel preparation, slag, CO shift, CO2, sulfur removal, CO2 removal. There, in most cases, we are offering physical absorption with silex soil, combined sulfur and CO2 removal. But this is dependent to the customer how we want to have that. Then we have the syngas and all the different things we can do with the syngas. Here combined cycle, but here coal to chemical, there's large variety of nice products which we can produce from such a plant. Another reference here, we are working here at the Texas Summit Clean Gas project. So we have a plant with 100 megawatts. And in the end, this is the carbon dioxide is used for enhanced oil recovery, and here we have a typical example for this polygeneration where the hydrogen is used in urea and ammonia production. In China, we have some activities, or major activities, better to say, where we have now 5 gasifiers in order to produce propylene here. And there are some more projects arising in China. Go there into detail. Because I want to focus here on the Siemens post-combustion carbon capture process. This has been proven, and absorption-desorption process is not a very new technology. So this is done 70 years ago in chemical processing and oil gassing industry, originally also in the gasification or syngas production. So this is, was not such a big step to adapt this to coal-fired power plants. The technology is quite easily scalable. Another advantage is that it's easy to retrofit, more or less easy. We will see that in the end. And at the moment, this is the preferred solution for this demonstration project, since it's not so very expensive. So, based our process on amino acid salt formulation, we will come to demands for this for such a new process. This is a picture of my former laboratory and co-worker, where we first developed and screened and chosen our solvent here. So we have a laboratory pilot plant, full automatically driven, where we chosen among the different options of amines, of these ionic liquids and whatever there was proposed. We tested it, and in the end we came to the conclusion that with regard to an environmental friendly process, the amino acids would be a nice option. So since for my origin I'm a chemist, I want to do with this some chemistry. What means that amino acid? Most of you will know ammonia, and in principle the amino acid is a derivative of ammonia. That here is the nitrogen, and acid function here is, you also may know, the structure of NEAR, which was also this basic amine group. And the thing is simply that these amino acids have the same characteristics like NEAR, but it is not volatile. And this is very important. We want to remove carbon dioxide from the air, but we want not to replace it by some organic chemistry where we are blowing amines into the air, from which arises new products. So this is quite important. We have no vapor pressure such a gas, so besides of entrainment, what can easily be handled with a proper design, no solvent will slip. These amino acids are quite stable to oxygen, more stable than the most of the amines, and amino acids are so-called building blocks of life. So they are naturally present, and so they are easily biodegradable, and no really danger goes out from really minor dangers, not inflammable, not explosive, no odor, no inhalation risk. All these things are connected to the low vapor pressure, low degradation, and in some environmental friendly substances. I guess this picture you also know this is a principal scheme of such absorption desorption process. We have here our flue gas, contact current, lean unloaded solvent flows here down and takes up the carbon dioxide via a heat exchange that comes to the desorption column where with steam the carbon dioxide is separated from the solvent and brought here to the utilization, and the loaded solvent, the lean solvent goes back here again, so we have a closed cycle. In the moment we are quite satisfied with the energy consumption in comparison with competitive processes with 2.7 gigajoules per ton. This is quite nice. Of course, you always have to say that this is not only the steam here, which we are calculating there. This is also energy, electricity, which is needed, for example, for clean solvent flash from here, which supports the stripping effect. This is sometimes neglected, and you need here some electricity to support the stripping effect, and then you get a quite low number here. But this is everything is included what you need to drive the whole process. And of course here you see no further washing sections, since the solvent itself, the active component, does not evaporate. Another nice thing is that since we have now amine in the vapor, we have no problems here with these aerosols. So these aerosols usually, or these aerosols which are reported sometimes are caused by condensation, and since we have no amino acid in the vapor, we cannot condensate them, and so we cannot form aerosols which has these amines. So, with all the advantages these amino acid salts have, we have a slight challenge, which luckily we mastered. Since we have no vapor pressure, we cannot distill the amino acid in the conventional way in order to clean the solvent in the reclaiming process. And therefore, we have invented this unique solvent reclaiming process for amino acids. This is especially it was my job for the last 2 years. We will see this is a two-step process where we separate the sulfur components, since this is the major impurity with regard to coal-fired power plants, and so it works to invent a selective separation process for the sulfur component, which in the end gives us such pure components that we even can sell it, for example, for fertilizer. And all the other things would also remain in the solvent over time, heavy metals, heat stable salts. Also, although we are quite stable, some degradation products also will occur within the amino this will then, with the waste stream, will be separated. So here it is once again somewhat more clear shown that this two-step process. This is not totally true because here only a small tear stream is necessary for the we call this the reclaimer 2. Here is the major stream goes here, and only a small tear stream must be worked up. And this is the conventional amine reclaiming system where you have to evaporate the amine, and it's always the problem that we have massive salt content here, and to run this properly with regard to temperatures and so on. Our process works nearly at room temperature. The highest temperature will be at 6 degrees centigrade, because we have to evaporate some water here, but this is quite low temperature and low energy consumption. We've tested this process not only in our laboratory. We have a pilot plant at the E.ON site near Frankfurt at Staudinger. There you see the FGD of the block 5 of their coal-fired power plant, and here we have our absorber and desorber column. This absorber and desorber column at the first glance seems to be quite small, but it is the smallest size where industrial packing material is reasonable to handle and gives us reliable data and information. And the height, this is important, is the same as large-scale process would have. So we see that this scalability of the experience we have here can easily to put on the large scale. We needed these data also, and also the data from the laboratory, in order to develop a simulation tool. As Lenu told you, have some knowledge in the simulation of physics behavior, which is in the end the basis for process simulation. So we developed a thermodynamic model of the solvent, of the energy and the loadings which we will achieve, and all this is implemented into commercial process simulation tools, S++, which we're using for a long time. And so we are able to simulate all these things, like we also can simulate the capture plant. And from that, these nice pictures come, where we have the planning of a whole plant with the carbon capture unit inside. And of course, the data which we gained here at the pilot plant and the data which we gained in the laboratory were used to validate our thermodynamic model. All these things we cannot do on our own, so we are not alone in the world. So we have looked for some strategic cooperations which we have found with the Master Institute, which is also nice because this is a potential or a really dependent customer for us. And but there's also now a scientific collaboration with the Master Institute, and so we are also working with them in a project for enhanced oil recovery. So we have a pilot here for 6 tons per day. This was planned for master, and is now in the decision how master will proceed with this. I don't know if you know, master has a quite ambitious target to have a carbon dioxide emission-free city, this master city, and this project is part of it. The second organization which we found was the TNO. The TNO is a very long time active in the field of utilization of amino acid salt solutions within CCS, and so it was sensible to put knowledge together, and so we are have a quite narrow collaboration with the TNO for the last 4 years. So that in principle I've said before, although we have really advances for a steam power plant with regard to the composition of the flue gas, the current projects are really the gas-fired power plants, where we have to do some homework and to adapt our originally was coal-fired power plants developed process also for the combined cycle power plant. And it was not surprising that we learned something about that the different compositions have a strong impact on the whole process, and in detail you have to adjust that in order not to have bad surprises. But this is now also planned. We have in Staudinger, we have the flue gas, use the flue gas of the Block 5, as I've told you, and now we also installed a gas burner there, so that we are producing our flue gas for our own, so that we have also a realistic gas-fired power plant flue gas for jet. And this is running now in collaboration with Monster later. So this was the first attempt in 2009. We started to adapt our post-cap process to gas-fired power plants, and have done here such a project about Stadtkraft. And now we are dealing here with Statoil, Casanova in Mongstad, where we are now in this technical qualification program, where we are challenged with our competitors, and where Statoil looks really very deep at which problems left. But so far we are quite in good shape with them, and we are discussing with them to build a cleaning plant here in Mongstad. So in between sum up, the post-cap technology is given by nearly zero solvent emission. We know washing steps here. We have a very limited solvent degradation. The reclaiming system is new and quite effective. And this is with regard to health safety by ready for, in principle, for large-scale application. So now I come to the last point. So if it comes to post-combustion carbon capture processes, always they say it's so easy to retrofit, but this is only partly true. If you look more in detail, many of the things in a already built power plant are affected by such a new process. That begins at the exhaust duct, that you have another composition here. The flue gas fan might have a new design because you have a higher pressure drop, which is sometimes underestimated. The steam turbine building, you have to extract here some of the low pressure steam. There must be simply the space to make it possible. Maybe the steam turbine has completely to be redesigned because the extraction and because the extraction also affects the whole train here. If you have if you changing the base load and everything. If you have other electrical loads here, cooling system would be different because the capture plant also needs cooling water. The wastewater treatment, condensate system, and nevertheless, or mainly the space you need for such a plant must be there. And so we done some studies, and from the TÜV Nord, now this is the technical regulation organization of Germany, who will also say that cars are safety and these things. They stated that our process or the design of our power plant is carbon capture ready, and this can also be used by customers or users for customers simply analyzing whether their power plant is ready for this or how they should build it. If there is a new power plant, how they should build it, that it is easy to retrofit. So we see here there is nearly half of the whole area or the space normal plant needs. We have to double this in order to have the space for such a post-combustion process. What are the main things to do? The stack has to be redesigned. As I said, the turbine building has to be high enough here, and we have to have enough space to get the piping properly. Yes, the steam turbine, the steam extraction, so the adaptation, the power supply has to be enforced, maybe cooling system, all the things I mentioned before. So I would like to summarize my talk. I hope I could show you fossil fuels will maintain a big share of the global electricity production. We will not be able to replace it by renewables or by nuclear power due to the public acceptance. We can offer a unique portfolio of high-efficient power plants, as well with pre- and post-combustion solutions, so that we can reduce or avoid the CO2 release. We see with our post-combustion technology, we have a new chemical absorption process, which is retrofittable and quite easy to handle. We have an outstanding environmentally friendly character, which is again very important after our opinion for the acceptance in the public. We could verify these advantages successfully in a pilot plant, and we are ready now for the demonstration scale project and working eagerly on this to realize such a demonstration.